Energy can be harvested from many different places. Some people use the sun to harvest it, other people use flowing water. However, a source that not many people look at is sound. Sound contains energy, and in this project I will attempt to harvest it and see just how much energy I can get from passing cars.
To begin, I will actually go backwards and begin with the parts already made, and then describe why they were made that way. With all the hardware laid out on the table, start by placing the oscillator between the two base plates and begin bolting all the parts together, not forgetting though the part that actually bolts onto the tripod. After hand tightening the nuts, draw a line where the oscillator intersects with the plates. Using just enough superglue, bond the piezoelectric wafers just above this line and solder wires to them. When reassembled, the nuts need to be firmly tightened to decrease the vibration dampening, which will mean more power. A full bridge or rectifier will be used to convert the oscillator's AC voltage into DC. In this test circuit, I attached the wires from the oscillator to the rectifiers and then to a pair of LEDs to see if the system would work. Sure enough, when strain is applied by flicking the end of each of the oscillator's beams, the corresponding LED would light up. This begs the question, how much power can this device actually make? Well, we can find out with these. Let's start by imagining the system as a basic circuit, where the DC comes from the oscillators and the rectifiers, remembering that the voltage in is still DC, shown here with actual recorded data. If values are given to the resistor and capacitor, a plot can be made using this equation. This equation shows that no matter the input voltage, big or small, the curve on the time axis will be the same. This means that we can calculate the input voltage. When testing, it turns out that my voltmeter draws enough current to actually affect my readings, which isn't a problem since I'll use an Arduino to record the voltage instead. To reduce charging time, I decided to use a 4.7 microfarad capacitor because within a second they reach near full capacitance. I now made the circuit with the new capacitors in place. Then I covered the back of the board with electric tape and hot glued it to the assembly. Since piezoelectric wafers operate off of mechanical strain, I made oscillators out of nylon to see if they would make more power, since they have a lower Young's modulus than steel or aluminum. I tested the circuit by flicking the oscillators, and sure enough, voltage builds up on the capacitors. And now I'll explain how I determined the lengths of these oscillators. First, I started by collecting the sounds of passing cars on a road with a posted speed limit of 35 miles per hour. After I collected that, I performed a fast Fourier transform or FFT to get the frequency domain of the signal. From the frequency domain, we can see what frequencies have the higher amplitudes. To take advantage of the higher energy within those frequencies, an oscillator would need to have a corresponding resonance frequency. For my experiments, I made a few oscillators to operate at a few different frequencies to see if there's any differences. To determine the beam length for its natural frequency, this expression can be derived from Euler's-Bernoulli's beam theory equation for a beam with a rectangular cross-section, where C is the constant for the vibration mode, which in this case is the first mode, L is the length of the beam, E is the modulus of elasticity or Young's modulus, I is the moment of inertia, A is the area, and finally Q is the density of the material. On the graph you can see when various materials are plotted, increased length results in a lower resonance frequency. The first experiment will be used to examine the frequency response of the oscillators. A 1 to 200 Hz frequency sweep will be played over 20 seconds to the oscillators. The voltage for this experiment was measured from the piezoelectric wafers to see the instantaneous voltages. Knowing frequency as it corresponds with time, a voltage and frequency graph can be made for each of the oscillators. From those, the resonance peaks can be measured to see the error from the earlier calculations. Since the experiment procedure was consistent, the plots can be compared where the aluminum second mode response was significantly higher than any of the nylon oscillators. For the field experiment, the device was taken next to a busy road where its voltage was measured with an Arduino for 10 minutes for each oscillator. The code is linked below. Reviewing the voltages on the capacitor, this device collected power. However, some gust of wind resulted in jumps in the voltages. Since we know that power is gathered by the capacitors, the line will eventually approach the voltage in. Adding a second polynomial tread line, a rough estimation of the voltage in is calculated. So back to the original question on how much voltage sound can make from passing cars. Well, with this device, turns out that it's roughly 0.2 volts.